All right, well, now that we've defined simple harmonic motion, we should get into how to describe it both in words and mathematically. Recall that a thing that moves under simple harmonic motion will have some sort of sinusoid as its motion. So here we have somebody who moves back and forth and tracks out a cosine curve. Let's take a quick look to remind ourselves what the actual form is that comes out. So here we're going to have Alice, and she's going to move back and forth horizontally, and we're going to track out her position on this axis. So we can see that as she moves back and forth, if we were to plot x as a function of t, we would get, maybe not surprisingly, this sinusoid. And we know that we can model that as a times cosine of 2 pi times little t over big T, where a is the amplitude. It's the distance in space that she moves back and forth from here to here. And on the graph, it's the maximum displacement, the highest points on the graph, as it were, highest point above 0 on the graph. That's A. And the period is the time it takes to repeat once, so it might be from here until it has gotten here, which will be 1 repetition. And so that would be t. For our particular values, I think we can see here that A is 2 meters. The time is the clock time, so I can't put a value for it. And it looks like the period turns out to also be 2 seconds. Didn't mean to make both of those be the same. But we end up with this kind of graph. And so we can see that we can model her motion as a pretty good cosine curve. Now, if she hadn't started at her furthest extent, then it would have been some other sinusoid, either a sine or some combination of cosine and sine. And we'll talk a little bit more about that later. But in essence, it's something like a cosine curve. This motion had the graph x equals a cosine 2 pi t over t, because little t over big T is what fraction of a cycle we've completed. Talked about this before. And of course, you always, as I said earlier, you often see this as x equals a cosine 2 pi f times t, because f is 1 over big T. And that's just a matter of convenience. There's no particular deep reason for writing it that way or not. Remember that if we wanted to get the velocity and we had a position versus time graph, you might remember from way back in the beginning of class that we could find the velocity by drawing the line tangent to the curve and then taking its slope. So let's do that for the cosine curve we just had. One note here is I reduced the amplitude from 2 to 1 just to make everything fit more nicely on the Desmos graph. So it doesn't throw off any of what we're about to say, but don't be surprised that Alice is moving a little bit less. So here we can see the blue line is the tangent line, and the red curve here is the curve coming out as I plot the slope of the blue line. So like for instance there, the slope goes to 0 just at the moment that it becomes horizontal. And you can kind of see what's coming out here as you plot it. It did get cut off a little bit down here, I'm sorry for that. But what's coming out is clearly also a sinusoid. It looks a little bit like a sine curve, but minus of it, because a sine curve would go up and come down. Here we're coming down and going up. But we can see a couple of important things. It has its own periodic motion. So let's go for a couple of bits. Let's do so this is a period. And of course it has its own kind of amplitude-like thing, which would be this. We have to be careful because that's not an amplitude. This is the maximum velocity it has. We might note that the period turns out to be 2 seconds. In other words, it repeats with the same period. That makes perfect sense, because if the object were to repeat its motion in 2 seconds but its velocity in, say, 3 seconds, that would break the definition of periodicity, because it means after 2 seconds it might be back to where it was, but it's not moving the way it was, so it hasn't repeated its motion entirely. All right, so we can say, to sum up again, that if our curve was a cosine, that our velocity looks to be a sine curve, but flipped, so a minus the sine curve. As an aside, if you know calculus, this actually makes a lot of sense, because you know you could just simply take the derivative, because the derivative of cosine of theta with respect to theta is minus sine theta. So we would expect to get a minus sine curve out. So it can be shown, either experimentally or via calculus, that the velocity and the acceleration in simple harmonic motion obey the following forms if, and we should be careful here, if x is something cosine 2 pi t over t. So if the x is a cosine, then the v is a sine curve with a minus sign, and the a is a cosine curve with a minus sign, all of them sharing the same period as they would have to. Your textbook has a nice little map, little tactics box they put up here, which is at least worth showing, that connects the cosines or sines, what sinusoids look like. Do notice that there are some special values at special times. Let's say we have the cosine 1, then at t equals 0 we start at a quarter of the period later we're at the origin, a quarter period after that we're at minus a, at 3/4 of the period we're back to the origin, and 1 period of course we've repeated. So notice that there's this alternating a, 0, minus a, 0, a pattern at the special quarter intervals. Be careful, it really is only the quarter intervals that have really nice things like that, but they are really nice to know. All right, so here we have a mass oscillates on a horizontal spring. Its velocity is v sub x, and the spring exerts a force f of x at the time indicated by the arrow. What is true? So when we're at this moment, we can see that the velocity should be 0. And the force, well, it's going to be, from here, it's going to be pulled towards the origin, which, since we're at a negative position, is a positive value, so it should be d. Here again is a little summary, that if we have the cosine case, then we get that we get cosine minus sine minus cosine, and they've actually figured out here, they list for us how to connect this to the amplitude itself, which makes sense, which is that it's 2 pi f times a. Again, if you know calculus, what's happened is we're taking a chain rule and pulling the 2 pi f out. If you prefer to have it in terms of period, then it's 2 pi over the period times a, and of course this is 2 pi over the period times squared times a. Your textbook has a somewhat involved discussion of the correspondence between simple harmonic motion and uniform circular motion, which they use to derive some of the formulas that we're talking about and to get relationships among the magnitudes of the position motion, the velocity motion, and the acceleration. And it's not bad, although your textbook, like most textbooks, puts a lot more emphasis on it than I think it's entirely worth, but it's certainly an interesting way of looking at things. And Flipping Physics, a YouTube series, illustrates that pretty nicely, so I strongly encourage you to go check out the video that's linked here. You can use the circular motion is simple harmonic motion to derive the velocity and acceleration exactly, to get those factors of 2 pi f that we showed up if you don't believe the calculus or don't know it yet. The guy who just did that, Flipping Physics, does a pretty nice job of doing those too, and I'm not going to walk through them because it isn't strictly necessary for you to know where they come from, but I do recommend, and we'll post to the website, that you take a view at these things because they're worth seeing.